back, students, to our second lecture. I'm sorry I'm still away at the ACS meeting in Boston, but I'll be back on Friday. So I'm going to give us our second lecture here today from Chapter 1. Remember to log on to the Blackboard site, go to the Mastering Chemistry site, and complete the two homework assignments that are due this Friday, the introduction and the math review. So last time we left off talking about metric prefixes, and we're going to do a little bit more work with problem solving and derived units today. Remember how I said a joule was a derived unit? It was kilograms meters squared per second squared. Well, there's several other derived units we use in chemistry. Area and volume are two of those. They're related to length. So if you remember, area is the length times the width, right? So we would measure this in meters squared. Two lengths times each other gives us, two lengths in meters times each other gives us meters squared, or any other unit of length you might have seen, square centimeters, or in metric units, square feet or square inches. An area consists of two lengths. If we have volume, that's length times width times height. So we have three different lengths, and so we get meters cubed as our SI unit for volume. However, you very rarely see cubic meters in chemistry. We often use cubic centimeters for volume. And the SI unit for volume is actually the cubic decimeter, which is better known as the liter. A liter is 1,000 milliliters. So our SI unit for volume is the liter, and we often see this in milliliters in chemistry. 1,000 milliliters, a liter is roughly a quart, so 1,000 milliliters is about a quart, or 32 ounces in English units. Now, one more thing I wanted to say about mass. Mass is the quantity of matter in an object. So remember that mass was one of our fundamental units. But interestingly, we measure this by weighing. And weight and mass are not the same thing, right? Weight is the force due to gravity, but mass is the quantity of matter in an object. So mass is actually, if you remember physics, F equals ma. The weight is the force, and the mass is that m in F equals ma. So a pound and mass are not the same thing, but we'll often convert them because we assume that we have this gravity on Earth. So mass, even though it's not weight, we actually measure it through weighing on Earth and assume that our gravity is constant. But mass is really about inertia. So here's a trick question for you, and see if you know the answer to this. If I have a mass, let's say I have a mass of 70 kilograms, what would my mass be on the moon? And it's a trick question, because your mass is the same on Earth as it is on the moon, as it would be in zero gravity. Mass is a function of how much matter you're made up of, not the gravity that you're in. So even though things in space have no weight, they still have mass. So you see those astronauts struggling to move big stuff around because it still has mass, it still has inertia, and they're still hard to move, things that have a lot of mass. We call those massive things, right? Things that have a lot of mass are massive. So even though they have no weight, they still have mass. So mass is a quantity of the amount of matter, and I didn't get a chance to say that in the last lecture. Another unit that we often use is temperature. And we would talk about temperature. You might say temperature is the hotness or coldness of an object. How much heat does an object have in it, and how does that temperature flow? And that's how we talk about temperature, heat flowing from hot objects to cold objects. So you're probably familiar with the Celsius temperature scale. I'm going to tell you how we relate Celsius to Kelvin now, and it's related through absolute zero. This is our starting point for the Kelvin scale, and we would say that absolute zero is 0 Kelvin. And it's just a shifting of the Celsius temperature scale. And Celsius, the absolute zero, happens to be minus 273.15 degrees Celsius. So if we shift that, we would say that the Kelvin temperature is equal to the Celsius temperature plus 273.15. So if we were to have 0 Celsius, our Kelvin temperature would be 273.15. So Kelvin is 273.15 degrees Celsius warmer than the Celsius temperature. Now we can rearrange this to solve for Celsius from Kelvin as well. So if I wanted to convert Kelvin temperature to Celsius, I would just rearrange this equation by moving this constant to the other side. I'd subtract 273.15 from both sides of that equation, and we have degrees Celsius would be equal to the Kelvin temperature minus 273.15. So we would subtract this to get the Celsius temperature. And that often can be negative, can be less than 0. So 100 degrees Celsius, if I were to convert this to Kelvin, the Kelvin temperature would be 100 plus 273.15. So the boiling point of water, 100 degrees Celsius, would be 373.15 Kelvin. So it's easy to do these temperature conversions between Celsius and Kelvin. Now Fahrenheit, which we use in the U.S. for our weather measurements for meteorological conditions, is not often used in science, but you'll see it a lot in common sources, so we need to know how to deal with Fahrenheit. Fahrenheit, interestingly enough, is based on the freezing point of water is 32 degrees Fahrenheit, and the boiling point of water is 212 degrees Fahrenheit. And you might say, well, that's really weird to base that scale with these numbers. But it turns out that the degrees between those two makes it so that you can evenly split them in half and in half and in half again. And so it makes it easy for the thermometer maker to make the marks on the scale. And that's why these Fahrenheit temperatures go between this range that may seem odd to you, but actually if you have to make little marks on a glass tube, it makes it a lot easier if they're evenly divided. So these numbers allow for these marks to be evenly divided on a thermometer scale. And the equation for converting Celsius to Fahrenheit is a little more complex. So if we want to convert Fahrenheit to Celsius, I take my Fahrenheit temperature, I subtract 32, and then multiply it by 5/9. And if I want to go the other direction, I would rearrange this equation. So if I wanted to move this 5/9 over here, what do? I multiply both sides of the equation by 9/5, cancels out on this side, and we get 9/5 degrees Celsius over here. And then I add 32 to both sides. So we would have our Celsius to Kelvin temperature would be a little bit different. We first multiply 9/5 by the Celsius temperature and then add 32 to get our Fahrenheit temperature. So a quick approximation that I learned in ground school to convert Celsius to Fahrenheit is to double it and add 30. Well, you can see where this comes from. 9/5 is almost 2. And if I double this and add 30, I get a rough approximation. It's not the exact calculation, but it's a quick way to double check, is you can double the Celsius temperature and add 30. And around room temperature, that seems to be a fairly good approximation of the Fahrenheit temperature. Another unit that we're going to use a lot that's a derived unit is density. Density is often mistaken for mass. Density and mass are not the same thing. Density refers to how much mass in a certain volume and not mass. So something that's dense is not necessarily massive. They're different things. So density is a relationship of mass over volume. So if density is mass over volume, what do you think the units of density will be? What are our units for mass? Kilogram, oftentimes in chemistry just a gram. And how about volume? Could be a meter cubed, could be a liter. Oftentimes for density we use cubic centimeters for volume. So an appropriate unit for density would be the gram per cubic centimeter. Or, as we'll see later, a cubic centimeter is the same thing as a milliliter, so that could be a gram per milliliter. So density describes how much mass takes up a certain amount of volume. As a standard, water has a density of about 1 gram per cubic centimeter. So this would mean that 1,000 cubic centimeters, that's 1 liter, would have 1,000 grams, would be about 2.2 pounds or so. And remember how I said a liter was about a quart, so that's about 2 pounds per quart, or as the aphorism goes, a pound a pint for water. So water weighs about a pound a pint. 8 pounds in a gallon. That means each gallon of water tends to weigh about 8 pounds. So water has a density of 1 gram per cubic centimeter. If you go to some of the metals on the periodic table, aluminum has a greater density, 2.7 grams per cubic centimeter. What do you think would happen if I put a cube of aluminum in water? Well, the aluminum is more dense than the water. So what would happen to that cube of aluminum? It would sink because it's more dense than water. So if that cube happened to be lighter than water, it happened to be less dense than water, then it would float in the water. So aluminum is more dense than water. And as we go down the periodic table, iron is even more dense than aluminum, 7.9 grams per cubic centimeter. And then gold is even more dense than that, 19.3 grams per cubic centimeter. So the further down on the periodic table you go, the more dense. And as we'll see, that's because you have more protons and neutrons in your nucleus in a given volume, so they tend to get more dense as you go down the periodic table. So density can be measured experimentally by weighing or measuring the mass of a given volume of substance. So let's say I take a beaker, and that beaker has a mass of 85.2 grams when it's empty. And I add 325 milliliters of methanol to this beaker, and the beaker, the mass of the beaker plus the methanol is now 342.4 grams. What is the density of the methanol? Well, if I want to know the density of the methanol, I need to know both the mass and the volume. The volume is easy, right? I added 325 milliliters. I probably did that with a volumetric pipette. So I know the volume that I added, but I need to figure out the mass. So how would I figure out the mass of the methanol that I added to that beaker? What do I know? Well, I know what the beaker and the methanol, the mass is, and I know the mass of the beaker empty. So I could just subtract those to get the mass of the methanol. So if I subtract the beaker plus the methanol, if I subtract the beaker from the beaker plus the methanol, I'll get the mass of the methanol. So that will be, let's take 342.4 minus 85.2 grams over my volume of 325 milliliters. And we get a density that would be 257.2 grams of methanol over 325 milliliters, and we get a density here of 0.791 grams per milliliter. And a milliliter is the same thing as a cubic centimeter. So how does the density of methanol compare to the density of water? Is methanol less dense or more dense than water? With a density 0.791, it's less dense. And so if methanol didn't mix with water so well, you would expect it to float on top of the water. The methanol has a lower density than the water. So density relates mass to volume. Right? So we talk about how the mass is related to a certain volume of the substance. Now, we can play some tricks with this by rearranging this. So right now, in this equation right here, I've got three unknowns. I have an algebraic equation with three unknowns. And I'll tell you, anytime we have an algebraic equation with three unknowns, if I know two of those, I can solve for any of the other unknowns. So in this equation, we knew mass and volume, and we solved for density. But I can absolutely rearrange that to solve for either mass or volume. So if I wanted to get mass all by itself on one side of this equation, how would I move volume over to the left side of that equation? I would just multiply both sides by volume. So if I wanted to solve for the mass would be density times volume. So if I wanted to solve for the mass, I would need to know the density of the substance and the volume, and then I could tell you the mass that I had. Likewise, if I wanted to solve for volume, I need to get volume all by itself. And when you have an equation like this, you can just switch these. Basically, what I'd have to do is multiply both sides by volume, and then divide both sides by density. And you guys can prove this to yourself. But volume is going to equal mass over density. So I have an equation, an algebraic equation, three unknowns in there. If I know any two of those, I can solve for the third. And I'll say this over and over and over again in this class. Anytime we have an algebraic expression, if I know all but one of the values, I can algebraically solve for the unknown value. We can move things around, rearrange the equation, and solve for the unknown. So let's take this equation and ask the question. What mass of methanol, how much methanol in terms of grams do you need to fill a 750 milliliter volume tank. So we're asking about mass, so we'll use this equation here. The mass is going to be equal to the density times volume. And we know our density, we just solved for it over here, so we'll use that, 0.791 grams per milliliter, times the volume, 750 milliliters. And I'm going to show you something here with the units in just a second. So if I multiply 0.791 times 750, we get 593. Remember our space probe, though. 593 what? We need a unit on that. Well, what happens if I multiply grams per milliliter times milliliters? Do you see how I have milliliters on the bottom here and milliliters on the top? These are just going to cancel each other out. And we get 593 grams as our mass of methanol. So whenever you have an answer like this in this class, it's not correct unless it has the units on it. So if you just gave me 593 on a quiz, that would be incorrect, and I would take points off for that because you didn't specify the unit. 593 what? Pounds, ounces, grams, milliliters, what? There needs to be a unit on it. So there's very few measurements in chemistry that don't have units attached to them. So your answer is not correct without that unit. And we'll talk more about how we do this unit cancellation. It's called dimensional analysis a little bit later in the class. So we solved for mass by knowing the density and the volume. Using the same density equation is mass over volume. So we can rearrange that equation however we see fit. Now, speaking more of measurements and reliability of measurements, because remember, chemistry is an experimental science. We do experiments, we make measurements, and we need to talk about the reliability of these measurements. Scientific measurements are reported so that every digit is certain. Every digit in the measurement is certain. I'll tell you a little bit more about that, what that means, except the last digit which is estimated. So what this means is, when I take a measurement and I give you a 593 grams, for instance, as a measurement, that means that I measured this to plus or minus the last digit, 1 gram. So I say, I am telling you this, that I measured this to a reliability of plus or minus 1 gram. That's what I mean when I say every digit is certain. I actually measured those digits. And I'm telling you the reliability of that measurement by the number of digits. So if you measure a length with a ruler, you might say that the length is 10.55 centimeters. And you would say 10.55 because on a standard ruler, you would have gradations on that ruler of 1 millimeter. Right? So you'd see centimeters, and then there'd be 10 little ticks on there for millimeters, and then this last digit is estimated. So I would say, well, it's halfway between 5 and 6 millimeters, so we'll call it 0.05 centimeters, or 0.5 millimeters, a half a millimeter, because it's halfway. So these digits are certain except for the last one, which is estimated. And so I would say that I have 4 significant figures of accuracy in this measurement. If I used calipers, For those of you who don't know who calipers are, they're those little mechanical, what do you call them? They're little teeth, and you can put them around a pipe, and you can clamp down on it, and they're much more precise an instrument than a ruler. So I might be able to measure this to 10.547 centimeters with calipers. So that extra digit is more precision in that measurement. And I'm saying I measured it with a finer instrument. So I'm implying to you, by giving you 10.547, that I used a finer instrument with which to measure that length than in the previous measurement. I have more digits here with which I am certain. And we call this significant figures. And this is important, again, because chemistry is an experimental science and it relies on measurements of different values. And we need to talk about the precision and reliability of those measurements. And significant figures is what we do. So 10.55 has 4 significant figures, but 10.547 has an extra one. It has 5 significant figures. So we're saying this is a more precise measurement with more significant figures. The more significant figures, the more precision you have in your measurement. So there's some rules for significant figures that we need to learn so that we can work with our measurements in our class. And we need these rules because it gets a little complicated when we start having decimal places. So our first rule, all non-zero digits are significant. So any number we have there other than 0 counts as a significant figure. So these 10.55, for instance, definitely has at least 3. And then there's some instances when that 0 becomes significant or not. We'll see that in a second. So 2, the second rule, zeros between 2 numbers are significant. So this 0 in 10.55 is significant because it's between a 1 and a 5. It's between 2 other significant numbers. So that 0 is significant. That means I measured that 0. It's really 10.55, not 11.55 or 9.55. That 0 is a significant digit. Zeros to the left are not significant. Zeros to the left are not significant. They're placeholders, or decimal point holders. So, for instance, 0.0026 grams has 2 significant figures, because these zeros to the left are just placeholders for the decimal point. They're not actual significant figures. So we'll see later that these don't imply any precision. It's plus or minus 0.0001 grams. And these zeros are not significant. Trailing zeros these are zeros to the right, may or may not be significant. So if they're after a decimal point, they are significant. And an example of this is 2.240 grams. So when I tell you 2.240, I'm telling you that I measured this to plus or minus 0.001 grams. I measured this 0, the the balance actually said 0. I measured that point. It's significant. So this has 4 significant figures. But if I had, say, zeros before a decimal, they may or may not be placeholders. Let's say I measured something very large, and it had a mass of 10,300 kilograms. Well, how do I know how precise that measurement is? Is it plus or minus 100 kilograms? Is it plus or minus 10 kilograms? Is it plus or minus 1 kilogram? I don't know. There's uncertainty there. So this may be 3 significant figures. It may be 4, or it may be 5. It's definitely at least 3, because of the 1 and the 3 and the 0 between those are 3. But there's a question as to whether either of those zeros is significant. And that we can resolve this fairly easily by using scientific notation. So if we were to write this as, in scientific notation, it would be 1.03. Let's say, for instance, I wrote 1.03 times 10 to the 4th kilograms. That would then be 3 significant figures. If I wanted to write this as 4 significant figures, I would write that 0, or as 5. I would write it as 1.0300. So this is 4 significant figures and 5 significant figures. Because remember, these trailing zeros after the decimal point are significant. They indicate you measure. So try not to leave any ambiguity as to whether a digit is significant or not, because it's important to your reliability of your measurement. Okay, we also have, in addition to measurements, are exact numbers. Now, an exact number have no uncertainty. So we have essentially an infinite number of significant figures because we know that exactly. So an exact number is anything you can count. There are 12 eggs in a dozen. If I have a dozen eggs that I buy at the grocery store, I can count them. There's 12 eggs in there. It's not a measurement because it's not plus or minus 1 egg. It's 12 eggs. It's an exact number of eggs. There are 12 eggs there. I don't have this significant figure consideration because there's exactly 12 eggs in there. So an exact number is anything you can count. Whereas if you have to do a measurement, then you have significant figure issues. But if you can count something, you have an exact number. The other type of exact number you have is a definition. For instance, the definition of the inch is now 2.54 centimeters. So there are exactly 2.54 centimeters in an inch. That is the definition of an inch. It's not 3 significant figures. It's infinite because that is a defined number. It's not a measurement. You measure the inch, but the definition is 2.54 centimeters in an inch. So this is an example of how we have exact defined numbers. Now let's do a quick calculation here to see how we use significant figures in calculations. Because we're often taking our measurements from the laboratory and then doing some kind of a calculation. And we have to figure out a way to keep track of these precision of these measurements, the significant figures, through these calculations. So the first rule is the least certain measurement limits the certainty of the overall calculation. like saying a chain is only as strong as its weakest link. A calculation is only as precise as its least precise measurement. So the lowest number of significant figures in your measurements is going to limit the overall calculation. And our second concept here is the final answer should have only one uncertain digit. So, for instance, let's say we're calculating the volume of a box, right? Length times width times height. And I'm going to make 3 distance measurements to figure out the volume of this box, and then I'll multiply the length measurement times the width measurement times the height to get the volume of that box. So let's say it's 15.5 by 27.3 by 5.4 centimeters. Thought you'd get me there, but those are all centimeters. So I didn't write them, but each one of those is a centimeter. Right? And if we multiply this together, and your calculator would spit out 2285.01, and what would the unit of that be? What would the unit of that volume be? If each of these measurements are centimeters times centimeters times centimeters, this would be cubic centimeters. So our volume that the calculator spits out is 2285.01 centimeters. This would purport to be 6 significant figures. That is, I measured the volume of this box to plus or minus 0.01 centimeters. And that's not right, because the least certain measurement limits the overall calculation. So which of these measurements, which of these 3 measurements, is my least certain one, and why? Which one of those do you think is the least certain measurement? Well, remember, the certainty is the number of significant figures. The more significant figures you have, the more precise, the more certain you are. So the one with the least number of significant figures is that 5.4 there. So that means that our answer, when we're doing this multiplication, can only have 2 significant figures in here. So I have to round this volume to 2, and it would be 300 cubic centimeters. Well, I would round this up because this digit is more than 5, is 5 or more, so that rounds up to 2300. But this isn't the best way to write it, because remember, I don't know whether those digits are certain or not. So I should write this in scientific notation. 2.3 times 10 to the third. I had to move my decimal point over 1, 2, 3 places. So that makes it 10 to the third. And I have 2 significant figures in that final answer because my least certain measurement only had 2 significant figures in it. So the overall certainty of my final calculation is limited by my individual measurement with the lowest certainty. All right, I'm going to stop here. And we'll continue on this on Friday. Don't forget that you have 2 homework assignments that are due on Friday that you need to complete to be ready for class. And then we'll have our first quiz, not this first Friday, but the second Friday, I believe that's September 3rd. We'll have a quiz over Chapter 1, and your Chapter 1 homework assignment will be due on that date as well. So thank you very much, and I will see you in class. I will actually be back from my meeting on Friday, and I will distribute the course syllabus then, or you can get the course syllabus off the Blackboard site. Thank you very much, and I'll see you on Friday.